Thank you, sir. And everybody can still hear me? Perfect. All right. So yes, today I'm going to talk about advancements in irrigation technology and their impact, or also the potential impact of that technology on water management. Just a little, again, background about myself. I'm actually native to Nebraska. I grew up in South Sioux City, which is northeast Nebraska. Following high school, I did come here and was fortunate enough to receive my degrees in biological systems engineering, focused on irrigation engineering. So it was the best place to receive those degrees, and I was very fortunate to have the opportunity to pursue becoming a faculty member in the department, and again was fortunate not only to apply but to get that position. So I'm stationed out at the West Central Research and Extension Center located in North Platte, shown right here, and I've been there for approximately 2 years. I first also want to start off by acknowledging my research team. We are very dedicated to the work that we do, so I'm very grateful for them. Our irrigation research technologist too, Turner Dorr. We have 2 graduate students, Himi Lowe, which is, he received his master's degree in biological systems engineering under Dr. Hiran. Jasraman Singh from India. And then we have our research tech and Bridget Dorr, our program assistant. So again, I'm very appreciative of them and what they do. Also, it's hard to do research without funding and the support to carry out our research objectives. So I always like to show some of the funding sources that have allowed us to collect this data, as well as the industry support in terms of them allowing us to have some equipment as well as services to further evaluate some of the technology in irrigated agriculture. So why do we irrigate? That seems like a very simple question, but simply speaking, if we don't have enough precipitation or stored water in the soil profile to meet crop water demand, we do have to supplement with irrigation. Now, in the perfect world, we would be able to provide that exact amount that would be required by the crop. That would require perfect quantification of crop water use, as well as our ability to quantify how much water is available in the soil to that crop before any water stress is imposed. Now, in terms of reality, that is very challenging to do. Therefore, there are really 2 alternatives, things that potentially could happen. One, we might not provide enough irrigation in certain areas or to the field itself. That can result in reduction in our biomass, our yield, the quality of our yield, and ultimately impact the economic return of our producers. We also can over-apply our irrigation, which can lead to some more of the environmental concerns, runoff, which leads to soil erosion, percolation of water and nutrients, which can contaminate our water quality or our water resources, anaerobic soil conditions, and then also pumping expenses. So in Nebraska, we're very fortunate in terms of irrigated agriculture. A lot of it is set up, again, you guys are probably quite familiar being in Nebraska, but we do have that longitudinal gradient in precipitation. So we go from that very semi-arid, arid in western Nebraska, 14 to 16 inches per year, all the way to the subhumid, greater than 30 inches in eastern Nebraska. Now, the one thing is exciting that as long as I've been in Nebraska, which is my entire life, there's no such thing as normal. So although we have these differences in precipitation, we are constantly being imposed upon us distribution and changes in the magnitude of water that we get throughout that season. So we do need to develop our management strategies to accommodate those. This is, again, stuff that you guys are probably quite familiar with, the distribution of registered irrigation wells. I like to show this just because we have a precipitation gradient doesn't mean we necessarily just irrigate more in the western part of the state. Relatively speaking, we also have to factor in other variables such as our soils and how productive they are, and our ability to actually have water source for our irrigated agriculture. When we look at the density, central Nebraska and the Platte River is very dominant, and when we look at this relative to our nitrate ground water contamination levels, we can see that there is a close correlation. So as we continue to develop our irrigation management strategies, we have the opportunity to maybe not necessarily mitigate, but hopefully prevent future groundwater contamination. Just a couple additional slides showing the consequences of sometimes if we excessively irrigate or insufficiently apply water. In terms of the lower portion of the page, that's just showing some of the impacts of water stress. It's important to note that water stress is a function of the duration as well as the magnitude of that water stress imposed on that crop. It can have issues, or it can lead to a reduction in leaf area, plant height, total biomass, grain yield, kernel weight, kernel abortion, and so forth. We also have situations where irrigation coupled with precipitation, we can have runoff and erosion. So this was an image taken by a technician in our research center in North Platte. We can see that basically the ditch just neighboring the field is completely filled with deposits of that soil. So again, we want to do our best to manage our resources so that we prevent that. When we talk about irrigation, again, it seems very simple. We don't have enough water, we provide that water, but reality is irrigation management is very complex. We have to factor in a lot of different things. So one, we have to look at the soil. What is the physical system that we're working within? What's our water holding capacity? Do we have any chemical properties that are restricting us? What is the climate doing? How is that relative to our crop? What crop we have, the hybrid, growth stage, its tolerance to water stress. Other management practices, for example, maybe tillage, that can also lead to differences in water use. And then also a big one is restrictions, and that can be both physical, so we might be limited in terms of our system capacities, maybe through in-season drawdowns or drawdowns that happen over time, as well as maybe we're under load management or even maybe a water allocation through policy. So when we look at those, we have to factor in all these as main effects as well as interactions, make a decision output, and then a couple days later or a week later, we have to do this all over again, knowing what we've done in the past and knowing what's potentially in front of us. So quite challenging. When we look at crop water requirements, again, we have to factor in that crop, what the climate's doing, what's the soil and its ability to supply water throughout that time period. So going from here, when we look at irrigated agriculture, we're always competing for that water. It doesn't always seem as obvious in Nebraska because in certain areas we do have a decent supply of water, especially our groundwater resource. Other areas are less fortunate. We're always going to be competing with cities, industry, recreational activities, habitat, and so forth. So it's important that we are good stewards of our resource. Just a couple more introductory slides, but I'm assuming most have seen the Ogallala Aquifer and changes in the saturated thickness. I again just like to show this on how this can lead to some of the physical changes in our restrictions in terms of system capacities, as well as how this might help navigate some of our policy changes that we have to then develop management strategies around. The Nebraska Natural Resource Districts are the ones that help us manage that and regulate our groundwater. They can do that through allocating groundwater, augmenting surface water, requiring flow meters. So we can see in that column right on the side differences in those allocation amounts. So before I get into some of the technology, I want to step back and look at what we've done in the past, primarily as a conventional irrigation, which is basically over decades we've really tried to improve our ability to uniformly apply irrigation. We do that based off of targeting either the average crop water requirement of the field or a higher economic threshold. So maybe there's a portion of that field that we're trying to target to increase our economic output. We have had considerable advancements in our irrigation technology, both in terms of the systems and their ability to get around and distribute water, as well as our ability to properly design systems based off of our soils, our topography, our changes within individual fields. So that's been a combination of both the systems, controllers, as well as sprinkler packages and how we design those. When we look at evaluating those, we still, this is very fundamental, and this is even important as we go into variable rate irrigation. Distribution uniformity. So the standard method is using more of a catch can approach, where we lay out catch cans, we measure how much water was collected underneath through those transects. We plug it into a distribution uniformity equation such as Hierman and Hein, and then we can go ahead and look at a cumulative coefficient, as well as we can look at the distribution along the length of the system. This provides us an opportunity to better evaluate our engineering and how we design that system, as well as our maintenance concerns associated with it. So when we look at that, I don't want to say necessarily new technology, but some technology that is being re-engineered to be more effective. So currently, mobile drip irrigation has become a pretty hot topic in the irrigation area. Simply, it is basically trying to look at conventional irrigation or using your irrigation distribution system and integrating drip technology. So this is some work that has been originally done, I think, back in the 60s in either California or Idaho. Again, was looked at in the 70s, and now NetFM has developed this product. This research is the reason behind looking at drip irrigation and center pivot is most center pivots depend on the location of the sprinkler package. We will tend to water the canopy so that water can get intercepted on the leaves and it could be evaporated into the atmosphere. Some will say that there is a potential benefit associated with that evaporation through a cooling effect. Others would say that the disadvantage of not getting that water into the soil profile outweighs the potential cooling benefit. So with the drip irrigation, the big thing that it's marketing is the reduction in evaporative losses. So we went ahead and wanted to go ahead and evaluate this technology. And this is complementing some of the research that's being done in eastern Colorado, Kansas, and the panhandle of Texas. So we looked at the mobile drip irrigation relative to sprinkler package, which was our existing Seninger IWABs. We did it under two different irrigation rates, full irrigation and a deficit, which received 60% of the full irrigation, as well as we looked at under two different residue levels to really try to put a further impact on the potential evaporative losses when we remove the residue. This is very preliminary results from last year. We basically did not find any differences associated with any production, whether that was yield or kernel weight or even biomass between the two systems, even if we were under full irrigation or deficit irrigation, as well as across residue levels. And that is pretty apparent when we look at this bar graph associated with the yields across the systems. Basically, we got our positive response to irrigation, but no differences across the systems. One of the things that we're really interested in looking at is more of the water dynamics. So how are those changing relative to these two system technologies? Are we going to see lasting effects when we go to year 2, 3, and 4, where we might not start with a full profile under deficit irrigation scenarios? So there's most certainly future research efforts that we need to better evaluate this technology, as well as the potential system constraints such as runoff, and how do we manage those and design that system with that in mind. So I want to kind of switch over to variable rate irrigation and talk a little bit about different types of variable rate irrigation, and then lead into the technology in terms of more of sensors. Variable rate irrigation is simply applying a variable depth or rate of water through the irrigation system. There's a number of reasons why this might be valuable. Simply, it might be trying to meet differences, spatial differences in crop water demand, soil conditions, and or other constraints. If we look at these two graphs that I just put up, if we start thinking of how a plant develops in the root system and where that water is being taken up, if going along through that duration, if we have variability in our soils, and when we have roots tapping into different soil depths in conjunction with variability in our soils, it might lead to us needing to look at variable rate irrigation. The question then becomes, is it economically feasible? A couple different types of variable rate irrigation is out there. Sector or speed control has been out for decades. Basically, it is speeding up or slowing down the system in the radial direction. The other two are more sprinkler-based controlled. The first is a fixed zone control, where we actually group sprinklers together. And the irregular zone control is basically getting down to individual sprinkler control, so you can pulse as you go in and out of these irregular shaped geometries. Just kind of highlighting a few notes on the speed sector control. One thing to keep in mind when we look at this as a VRI technology, it does not alter the duration, but it does alter the application intensity. So when we look at that in terms of engineering design, it will not affect the sprinklers, the system curve, and or the pump performance curve. So in this little schematic, if we go and we want to put on an inch or 25 millimeters, by speeding up the system, we will actually get a lower depth of irrigation, but it will not change the intensity of that application. So when we're actually looking at this relative to infiltration characteristics of our soil and our potential for runoff, this might not necessarily satisfy a reduction in runoff or a substantial reduction in runoff depending on the constraints. Sprinkler control basically is equipped with a series of solenoid valves which basically allow us to pulse on and off that water. So just simply, if we group them in banks of sprinklers, that's more of the fixed zone control as compared to individual sprinkler controlled. I have a video just kind of highlighting how that would work. Basically, we can see that one's on, now they're both on, and then the one that was originally on turned off. So again, it's just simply looking at it in terms of those valves pulsing. Apologize. When we do this, manufacturers have been really good about designing controllers to actually accommodate this. As you can imagine, if we start shutting off a large portion of the irrigation system, we could have an issue in terms of water hammer. So it's important that they have appropriate algorithms built into their controllers so that they can stair-step the turning off and turning back on that water so that we don't have those major oscillations within that system. When we look at pulsing, assuming that we have a fixed speed control, now we're actually looking at altering the application intensity and not the duration. So this might better satisfy potential runoff concerns as compared to the speed or sector control. Just a few pictures now. So this is one of our variable rate irrigation systems in Big Springs, Nebraska. It's about 10 to 15 miles northeast of the northeast corner of Colorado. As you can see, spans 1 through 6 are on. Spans 7 and 8 have turned off. The way that this works is an old farm scan 7000 series. Basically, it has our controller, which is located on the tower 6, and it communicates with a primary valve associated with each span, which is located in the middle. When it activates that span, it uses hydraulic lines to basically open and close all of these secondary valves, which are associated with those sprinklers. So as we start doing this, we will turn on and adjust that main primary valve, and that will go ahead and in turn alter the bank of sprinklers for that span. And this would be an example of an individual sprinkler controlled system. This is the one that we have located at the Stump Wheat International Research Center in Grant, Nebraska. And it's, again, you can identify the solenoid valves located for each individual sprinkler. One note I do always like to bring up, variable frequency drives. This is a technology that has developed over the years, and this is really allowing for the opportunity for variable rate irrigation depending on the magnitude of change of pressure or flow rate. So as you can imagine, if we start shutting off a large grouping of sprinklers on our irrigation system, we will drop that flow rate, which will cause the pressure to increase, and that will be unnecessary pressure on our pumping plant that otherwise could be reduced to save energy expense. So the question really oftentimes is it not necessarily a physical, but rather an economical value of doing this, unless we get to extreme levels where we have over pressurizing of our systems. So now to get to more of the technology, really one of the research goals I think I share with a lot of different irrigation researchers is basically how do we look at improving irrigation and nitrogen use efficiency, and we want to do that in a way to enhance economic return and prevent environmental degradation. So I highlighted a few different areas of research topics that we would like to address in my research team. So one, how do we reduce uncertainty in measuring or estimating of crop water and nitrogen requirements? How do we account for spatial and temporal differences in these water and nutrient requirements across the field? Then more on the engineering side, how do we actually design the systems to appropriately apply these as efficiently as possible to minimize our losses? And then ultimately, how do we develop management strategies to concurrently manage irrigation and nitrogen? And I highlighted fertigation in there because that is an opportunity for us to really start to better manage our nitrogen within our irrigation system. Here just highlights a lot of different information that's valuable for irrigation management. So although this is more, future slides are going to be talking more about the technology, it is important to think of other data sources that could be coupled with technology for us to really pull value. So that could be historical records, soil properties, whether that's using publicly available data from NRCS, soil samples that you collect on your field, or maybe EC mapping. We can look at topography. Nebraska is fortunate. We have most of our area with LIDAR as a elevation source. Field conditions. Then we get into some of the sensors, monitoring soil water status, plant status. We have a series of crop modelers that are developing modeling tools to better give us an idea of growth stage and potential advancements of those growth stages into the future. And then I also like to highlight telemetry, both in terms of monitoring our sensors, but also telemetry in terms of our irrigation systems. Being able to actually turn and on or off our system based off of, for example, maybe a precipitation event, you can go ahead and adjust appropriately. So I want to talk a little bit about some of the data sources and technology that's being used. So this is very much with variable rate irrigation as apparent electrical connectivity. It is commonly used for trying to delineate zones for irrigation. It is one of those, the reason why it's commonly used is it's relatively low cost and easy to measure, and it can act as a very nice proxy of important soil physical and chemical properties. One of the challenges associated with it is EC is a function of or susceptible to multiple factors, not just the ones that irrigation engineers are interested in. In terms of irrigation, we very much are interested in more of the physical attributes of the soil, so water holding capacity. So we need to be able to better identify and remove the dynamic factors such as temperature, soil water content at the time of measurement, and then highlight again the ones that we're interested in. And I know Dr. Franz is here, and his research team does a substantial amount to better improve this technology. Again, when we look at EC response curves, we always have to keep in mind that plants are not static. They do grow. The roots are always changing. The mass and where that water and nutrients are being taken up are different. So how do we start looking at what EC products or what depths are we interested in relative to the crop growth and where our water is being taken up at? This graph is just showing some work by Sudduth back in 2005, showing homogeneous soil. So when we start getting into more stratified soils, again, how do we go ahead and break this apart and make it useful for zone delineation for irrigation? Some work that has been done by myself and Dr. Swat Ermach, we did look at EC relative to some hydraulic properties in clay center. We did find stronger linear relationships at the near surface and more curvilinear at the subsoil. Similar results in terms of the linear response was observed by Headley and Ewell in 2009. Dr. Heron could probably correct me if I was wrong on that one. So there's been some successes in using this for basically being able to identify differences in soil physical properties. And then there's been probably equal amount of unsuccessful opportunities. For example, one of our fields in North Platte, or in our rural area, we've been unsuccessful at using it. So we really need to, again, go back and say, how do we use this and what missing information can we make it more appropriate and stronger? So now I'm going to spend quite a bit of time talking about soil water monitoring equipment and where we've gone over time with that to kind of give an idea why this sensor technology is very valuable for irrigation management. I like to go ahead and show a diagram of water or of what the soil would look like. If we think of it in terms of a bucket, our saturation to field capacity, so that water is more or less not available. It's available for a short period of time. When we get beyond wilting point, that water is not available for the crop uptake. So we're really managing within the bounds of field capacity and wilting point. When we look at that, we break that up into two separate portions. One is really where we try to manage to stay out of water stress conditions. So we can really think of this break point as a trigger point, and we trigger based off of our irrigation system design. How long does it take us to put on water? And then again, to stay out of any water stress conditions. So as you can imagine, if we have confidence in soil water technology, monitoring technology, we can use that to basically guide us to stay above that threshold. When we get close, we can trigger our irrigation and stay above. The challenge becomes there is a huge amount of differences in sensor technology that's out there on the market. Here are some of the in situ companies that range. These are going to be everything from time domain reflectometry, capacitance, electrical resistance, frequency domain reflectometry, and so forth. Here is some of the visuals of what some of these sensors look like. These are more of the point-based ones, not multi-sensor probes. One thing that's very encouraging is these sensors are actually oftentimes measuring more than just water content. And I would say that most of the time when they measure temperature or electrical conductivity, those sources of data are underutilized. So opportunities and advancements going forward is how do we use that information, whether it's for irrigation or for other agronomic practices. And then providing more value to the producer is always critical to make that more cost-effective for adoption. We did a field study this last year evaluating 16 different types of sensors. Again, they're ranging across both water content-based sensors as well as tension estimating sensors. So I'm not going to necessarily name them all, but we did this in North Platte under soybean production. This is what we actually observed in terms of the performance of factory calibrations at different depths. These yellow dots, these are field calibrated neutron attenuation measurements. The averages, the error bars are really the min and max of 4 observations located in that area. We have strong confidence in that neutron attenuation where we had a R-squared value or coefficient of determination of 0.99. When we look at this, automatically, first thing most people are going to see is every sensor, on average, overestimated water content. Depending on how you actually manage your irrigation using sensor technology, that can become quite troublesome. In Nebraska Extension, we do make recommendations on water holding capacity and potential thresholds for sensors to trigger. So if we're looking at absolute values or the values that are reported by a sensor, if it is consistently overestimating, we might think we have more water available. That's where the important thing is not just looking at the absolute value, but also looking at the trends, so the relative change. We do look at several different calibration techniques. Every extension opportunity I get talking about sensors, automatically, usually one of the conclusions is we need to calibrate these sensors. Then automatically, first question is, how do we do that in the field and not at a laboratory setting? So there are a few different techniques available. We can look at offset calibrations, 2-point calibrations, regression responses, retention fitting, and more traditional laboratory-based techniques. Just as a schematic of what an offset calibration would look like and would probably be most likely the easiestly adopted by consultants or industry itself, is basically if you go out there and do a 1-point calibration, so you collect using gravimetric or a well-calibrated neutron gauge, you identify the magnitude of difference between that sensor and the reference value, and then you go ahead and offset all future points based off of that value. So now the challenge becomes, we've made 2 very key assumptions by doing that calibration technique. One, it's based off of a regression response that is linear, and that the slope is equal to 1. I'll show in the next slide that that is not the case for all sensor technologies, at least in the soils that we tested. So when we do that, if we impose this calibration technique, we might actually find it to be worse off than if we would have stuck with a factory calibration. So looking at regression responses, this is practical maybe on a research setting, but the temporal density data is not practical for a producer. If you're going to be collecting this much gravimetric or neutron attenuation, there's no reason to be using some of these other techniques. But when we look at this across these sensors, we do see differences in linear responses as well as quadratic responses, and how some sensors are more sensitive at different water content ranges as compared to others. Knowing that information and being able to test it across multiple years will provide us some value in knowing how those factory calibrations perform under those soil conditions. This is some data that we've done in the lab using more of traditional calibration techniques. Basically, we remove soil, we dry it down, we put it through a 2-millimeter mesh, and then we repack it to a desired bulk density. You can see that these responses are quite different than the ones shown in the field setting. Some of the sensors are quite close, other sensors are not. So there's definitely a difference based off of whether we have structure or intact sensors, which has led us to a pilot study that we just completed, basically looking at, are there certain sensors that we need to be doing intact soil cores in terms of laboratory calibrations relative to the more traditional repack. We can see that the drying curves shown here, there's definitely a difference in drying pattern, which would mean really nothing in terms of sensor calibration. But we did observe a slight reduction in terms of our repacked sensor response as compared to the intact. I haven't had a chance to test whether or not that would be significantly different. However, we did find slight differences associated with it, and this was in one of our more accurate based technologies. Kind of closing up on some of the soil water monitoring research that we're doing, we are also interested in how do we develop more appropriate calibrations across the state of Nebraska. Oftentimes, again, if we develop a calibration in our Cozad silt loam in North Platte, the farmer that's an hour down the road under maybe a Kuma silt loam, he might say, is that even valuable for my, my soil conditions? So we selected 5 soils that ranged in terms of clay content, going from 5% all the way up to 50%, which is the Wymore, which was located out at Rogers Farm. Basically, here we want to be able to see if we can use some of the soil textural properties and use those as adjustment factors to alter the calibration coefficients for a producer. So we're doing this research across a couple different sensor types, and we're also going to induce some salinity effects to see, again, how these sensors are going to respond across the soils and salinity levels. Getting into some of the other instrumentation that's currently being investigated and used for irrigation research, here are some research questions that my PhD student put together. So really, how do we collect and analyze data sources that range in spatial and temporal frequency? And how do we do that in a way to inform both variable rate irrigation as well as conventional irrigation? And lastly, as we start altering our irrigation requirements, how do we start altering our, or do we even need to consider the impact that would have on nutrient availability? And if so, how do we go about concurrently managing that or improving that management between the two? So really this, I'm going to present some slides in terms of different sensors that were used that ranged in spatial and temporal frequencies. We did a lot of this under an experiment that was conducted at our Brule Water Laboratory. We did it under 2 different soil types, very gravelly based. So we maybe had 6 to 12 inches of decent soil on top and then went to pretty much pure sand and gravel to areas that had much nicer loam and silt loam soils. We went from full irrigation to our rain-fed production. So this is the irrigation system that we performed that research under, again, individual sprinkler controlled. So just kind of going through on some of the different sensors. So we looked at a meshed network of capacitance-based sensors. So we selected AquaCheck. Basically, they have the ability to radio communicate to a central hub and then using cellular connection output the data. We went ahead and used still the standard method for water content determination using neutron attenuation. And we were very interested in looking at temperature responses. So this is infrared radiometers, so IRT sensors, and we installed those directly above the canopy. So now just what some of this data would look like, AquaCheck, they actually provide their raw data in terms of scaled frequency, so we would have to look at factory calibrations as well as our own developed calibrations to adjust that. I know that some companies are starting to look at if scaled frequency is an appropriate output to scheduled irrigation rather than trying to adjust it to a water content. Here is what some of the total water would look like across these different treatments. So the gravelly, non-gravelly, substantial differences in water holding capacity. And then at the end of the season, October 3rd, we can see the treatment effects associated with that water availability. So really in terms of how this data is looking and how some of the limitations associated with it, when we look at IRTs, we would like it to basically say, okay, this one is under water stress condition and it's showing that through a higher temperature on the canopy. The problem is we do have diurnal effects associated with these sensors. So as you can imagine, late at night and early in the morning, we're not going to see relative differences. But then at the peak periods in the day, that's where we start to see a separation under extremely water stressed crops as compared to fully irrigated crop. Some of the research efforts to try to make this useful, a lot of research is being done by the ARS group and USDA ARS down in Bushland. There's also our colleagues in Colorado State University, both in their ARS division as well as CSU. Basically, there's a couple different approaches that are being used. Some are looking at the difference, the magnitude, so how much difference are we seeing between the two? How is this relative to a set threshold? And then others are starting to look at the total duration of stress above a certain threshold. So that's basically looking at the gap or the length across that gap above a threshold. So we also looked at some aerial imagery that was provided by Air Scout or Egg Valley. So this is just basically what we can see visually. You can definitely see artifacts of soil variability, and then later in the season we see the artifacts of our irrigation treatments. When we look at it in terms of camera taken directly above the crop canopy, we do see differences in that senescence, canopy closure. Again, all of these are going to lead into most likely differences in water requirements. So really to get to more of the interest would be the thermal band or the thermal imagery that they provide us. As shown here, we did take out a handheld camera to look at the relative difference because we're interested in the spatially dense aerial imagery and how that could be used. So when we think of aerial imagery, for the most part, its limitation is in terms of temporal frequency. And then when we look at a point-based measurement, we're perfectly fine on temporal density. We're affected by the spatial density. That's why we've looked at how do we integrate maybe looking at point-based IRTs relative to aerial imagery. So we had 12 different IRTs scattered across those irrigation treatments. Here are 3 measurement dates associated when they flew over our field. We can see there was a close correlation earlier on in the season, and we did get some separation in August on the 12th and on the 22nd. Couple notes, our aerial imagery we did see that had lower values of temperature. We also noticed that the observed range was also more narrow. When we look at trying to couple these, again, we have to start to think of, if we look at point-based measurements, we can better identify that diurnal fluctuation, and how does that couple with our aerial imagery. Again, if we use satellite, aircraft, or drones, they're going to be taking a snapshot in time. So again, where are they sitting on that length of the curve at that point of measurement? So I know that quite a bit of research is being investigated in addition to our research. This is some collaborative research with Dr. Heron, Dr. Neal, as well as their graduate student, Perdette Barker. So they were very interested in also developing remote sensing techniques for irrigation management. They did quite a bit of research in Meade. Now Meade presents its own unique challenges because we're on a different precipitation area. So we went ahead and complemented their experiment at our Rural Water Laboratory located, again, about 10 to 15 miles from the corner of Colorado, as shown here. This field is perfectly suited for variable rate irrigation because it is nearly impossible to figure out what's going on. You can see the LiDAR data, the topographic map. We have elevation differences exceeding 100 feet. We have that translates into a slope that, again, is in above 10 to 12%. That slope has been primarily the driver of some soil variability. So again, we go from 8 to 12 inches of topsoil to pure gravel. In other areas, we will have 6 feet of nice silt loam soil. So that was the test bed that Dr. Heron's group had to work with. So we're going to present just a little bit of the research findings on that. I'm not an expert in the modeling that was used to do this, so if I'm slightly off, I might make Derek stand up and provide us that output. But basically what they did is using remote sensing, they are relying on Landsat imagery. So when they do that, they're looking at it really doing 2 things. So they have crop reflectance, crop coefficients that is guiding a 2-step ET approach. They do that and they run their water balance. Now they also use the Landsat imagery to do a two-step energy balance. So basically they use the energy balance to adjust the coefficients for our 2-step ET approach, and then they run the model. The nice thing with the crop reflectance coefficients, those can be guided based off of prior understanding and knowledge of crop coefficients by other researchers. This is the irrigation system that was performed. Again, it's an individual sprinkler controlled VRI system by Zematic. This was last year's layout in terms of experimental design. So we had the remote sensing based VRI treatments versus a more uniform based using neutron attenuation. So when we look at that, we also blocked it on available water holding capacity areas. So some of the preliminary results, this is what we were able to observe in terms of differences in irrigation across those 2 management strategies. Conventional had about an inch less irrigation on average as compared to the remote sensing VRI approach. When we look at this, really the range went from 324 millimeters to 365. When we translate that into what was the difference between the yield, we did not observe any yield differences across those 2 treatments. some of the primary findings, which is very critical, is one, obviously the resolution of remote sensing products, so whether it's Landsat or drones. So Dr. Wolt, I believe, is in here that's also involved in that research. Can we increase the frequency to have better guidance between the two? And also, how do we start looking at coupling instrumentation to better guide these models? So that's where plant-based or soil-based sensor technologies can be very valuable. I have two last slides. We also are very interested in fertigation research. Again, just because we focus on irrigation, we understand that there's a close correlation with nitrogen and the movement of nitrogen within the soil. This is some research that is being, the lead PI led by Dr. Brian Cranky in partnerships with Drs. Ermach, Ferguson, Shaver, Shapiro, and Gluen. So we're doing this research both in Clay Center as well in North Platte. That research, I'm not presenting any of the findings. We started it last year. Basically, we have a series of different management strategies. So how do we actually schedule fertigation? Then the next question is then how do we design engineering applications to actually get that onto the field? So that's where variable rate fertigation could be of value. So I see this in a couple different scenarios. So I just wanted to put those out there. So one, we can start looking at variable rate fertigation under two conditions. If we have a variable rate injection pump, which are currently developed and available, can we look at uniform irrigation applications by variably applying our fertilizer? And if so, how do we do that? And then also, how do we variably apply our water if that is maybe our constraint we're working under, but yet we want to have that uniform and applied? So both of those, I think, are tangible in terms of what we can achieve. The next one is going to be a little bit more challenging, and that is how do we start looking at, if we have a constant injection fertigation pump, how do we do variable rate fertigation through our VRI technology, whether that's sector control or sprinkler control. So with that, I very much appreciate the opportunity to be here to talk a little bit more on irrigation technology, and I'll entertain any questions.
Are there any questions?
Nice talk. My question is your initial slides when you mentioned about the sources of uncertainty. So what do you think is the main source of uncertainty in, let's say, defining first what kind of a technology you choose, and then the second would be about the management of that particular technique?
Yes. So in terms of uncertainty and management, so when we look at uncertainty, we have to rely on what available sources of information we have, whether that's from a sensor or if it's public information or if it's even generated through laboratory samples. Anything that we do for the most part is through some kind of estimation approach or quantification that is susceptible to error. Whether, again, all of the aforementioned that I mentioned. So there are uncertainties there. Really some of the more challenging uncertainties, anything in terms of the natural environment, we are very limited in our capabilities to manage everything. So if we put something in one area, how is that relative to another area? It's impractical to maybe do soil moisture-based sensing using capacitance probes across an entire field. So those are some of the levels of uncertainty.
So following up on that, you want to manage areas, but often your measurements are point sensors. What are some strategies you're using to be more confident in your point estimates versus the areas that you actually manage nitrogen and water at?
Yes. So when we look at management zones, that's where some of the zone delineation techniques are very critical. We want to try to basically group on attributes that we feel are confident. That is a primary concern associated with variable rate irrigation if we're trying to go down to management zones. The next question that would follow up, that I would imagine that you would ask would be, Even on uniform irrigation, if it's a point-based measurement, how do you appropriately use something that is sensing a 4-inch diameter and extrapolate that to 120 acres? That is something that we have to work within the confines of the technology that we have available. We have to basically do our best to provide enough sensors that we feel confident that we can get a more accurate value under the financial limitations. So to be honest with you, there's not really a good answer to that, and that's why we have to continue our research efforts. Yes. So if a producer asked us, basically what we would always recommend, normally most people will adopt one sensor or a series of sensors in one location. We, at minimum, would like to see at least two sets of sensors per management area. So if you're uniformly irrigating one area, I normally recommend putting a sensor at the beginning and end of where you start your irrigation system, so that you're always being able to have an identifier of the wettest part of the field and the driest part of your field. So in terms of research, obviously then it becomes more of a statistical question in terms of what accuracy level and our ability to manage that. So how many sensors we need to have more of a true mean. So. Yes, so that is a very large range. So I know sensors are down. Some of them are $30, and others are $2,500. Really, so one of the things, again, we do a lot of extension talks, and oftentimes we talk about soil moisture-based technology. When we look at that, we have to factor in more than just that point-based measurement. What other information are we going to be provided? So a lot of the companies do provide some additional resources in terms of suggested trigger points. They also maybe will help facilitate the installation of the equipment and potential guidance on how to actually evaluate that. So really, in terms of an economics, that's up to individual producers on what they deem to be the most valuable from these technologies. One thing that we are developing in partnership with the ag economist out in North Platte, Matt Stockton, we are looking at trying to better put some economics to some of this technology adoption so that producers have a little bit more confidence on what sensors should they be selecting based off of what they deem to be valuable to them. So.
Do we have any more questions? All right, well, let's give Dr. Rudnick another round of applause.
Thank you.